Okay, so let's look at row spaces. Now, the row space is a space that is spanned by the set of vectors of any given matrix that correspond to the rows of that matrix. So let's take some matrix A and let it equal to 1, 2, 3, 4, 8, 12. Let's take this guy. Now, we know that the rows of this matrix are, let's call them, looks like B, row vectors, and we know that these vectors correspond to the rows of A. Now, so we can say that the row space denoted as Rs of A is equal to the span of the set. That's going to get really ugly. Equal to the span of R1 and R2. I'm just going to write R1 and R2 because it's easier. Which means that any vector in the row space of A can be represented as a linear combination of these two vectors. So that is the basis of a null space. No, that's not the basis. That's the basis, the fundamentals of a null space. But let's look at the basis of a row space. Sorry. Let's look at the basis of a row space. So now we have our matrix A. To calculate the basis of any given matrix, of a space defined by any given matrix or by any given rows, it is usually helpful to reduce it down to row echelon form in some way. So let's reduce this, and I can see that this row is, the second row is a multiple of the first row by a factor of 4. So I'm going to take negative 4R1 plus R2 and take that into R2. And that's going to imply 1, 2, 3, 0, 0, 0. Now the basis of a row space of matrix A is all the non-zero rows. So in our case we have only one here. So basis for the row space of A is equal to the matrix 1, 2, the vector 1, 2, 3. So that is our basis for the row space of A, which means that any vector in the row space of A can be represented as a scalar of this. And this is easy to see because we know that the row space of A is equal to the span of the rows of A. So we can show, which implies that any vector V in the row space of A is equal to C1 times vector R1 plus C2 times vector R2. But we know that R2 is just 4 of R1, which means that C1 R1 plus 4 C2 R2, which means C1, and then we could combine 4 C2 R1, sorry. We can take R1 out, C1 plus 4 C2 R1, and then C1 plus 4 C2 is just some other scalar. So now we have this reduced row echelon form matrix, and the basis for this matrix is the same as the basis for this matrix. The basis for the row space of this matrix is the same as the basis of the row space for this matrix, which means that Rs of A is equal to Rs, and let's call this matrix here matrix R for reduced row. So R, and so my claim is that the row space of A is equal to the row space of R. Now that's a very bold assumption, very bold assertion, so let's prove that. proof right here. So I'm going to state this theorem here. The row space of a matrix A is equal to the row space of its reduced row echelon form matrix. Now, whenever you're showing that two spaces are equal, you have to show that one is contained within the other. So we have to show, one, that the row space of A resides within the row space of R, and two, that the row space of R resides within the row space of A. That's how you do what's known as a double containment proof. You have to show that one is in the other and then vice versa. So let's start with proposition 1. The row space of A is inside the row space of R. And in order to do that, you have to take any arbitrary element of a matrix. So let's set our matrix A to be equal to the row vectors A1, A2, all the way down to AN, just some arbitrary stuff. And same thing with the reduced row echelon form version. So we know that the row space spans, the vectors in the row space span, the column vectors span the row space. So we know that A1 can be represented as any linear combination of the other rows, because you can get from this matrix to this matrix by elementary row operations, which means that I could say that A1 is equal to K1R1 plus K2R2 plus plus KNRN, where Ki is just some real number. So this means that check that. And the same is true in reverse. So this is actually what we should show first, that because you get from here to here by elementary row operations, this is equal to we know that R1 is equal to, again, any kind of linear combination of, and so on. We know that R1 is equal to a linear combination of the rows of A. So therefore, we know that row space of A is contained in the row space of R. And as I showed first, because of the reverse, you could just reverse the elementary row operations and you're going to get back to A, which means that the row space of R is contained within the row space of A, which means that the two row spaces are equal. So that is a short video on row spaces. Up next, we're going to talk about column spaces and the null space and how to calculate the basis for those.